Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Section 4, Consistency of the notion of points, lines, and plane at infinity. We will now reduce the question of the consistency of our new terminology to that of the consistency of an algebraic system. For this purpose, we presuppose a knowledge of the elements of analytic geometry of 3 dimensions. In this geometry, a point is equivalent to a set of 3 numbers. The totality of all such sets of numbers constitute the analytic space of 3 dimensions. If the numbers are all real, we are dealing with ordinary real space. If they are any complex numbers, we are dealing with the ordinary complex space of 3 dimensions. The following discussion applies primarily to the real case. A plane is the set of all points, number triads, which satisfy a linear equation ax plus by plus cz plus d equals 0. A line is the set of all points which satisfy 2 linear equations, a1x plus b1y plus c1z plus d1 equals 0, and a2x plus b2y plus c2z plus d2 equals 0, provided the relations a sub 1 divided by a sub 2 equals b sub 1 divided by b sub 2 equals c sub 1 divided by c sub 2 do not hold. Now the points x, y, z, with the exception of 0, 0, 0, may also be denoted by the direction cosines of the line joining the point to the origin of coordinates and the distance of the point from the origin, say by L, M, N, and 1 over d, where d is equal to the square root of x squared plus y squared plus z squared, and L is equal to x divided by d, M equal to y divided by d, N equal to z divided by d. The origin itself may be denoted by 0, 0, 0, k, where k is arbitrary. Moreover, any 4 numbers, x sub 1, x sub 2, x sub 3, x sub 4, with x sub 4 not equal to 0, proportional respectively to L, M, N, 1 over d, will serve equally well to represent the point x, y, z, provided we agree that x sub 1, x sub 2, x sub 3, x sub 4, and cx sub 1, cx sub 2, cx sub 3, cx sub 4 represent the same point for all values of c different from 0. X sub 1 equal to cx divided by the square root of x squared plus y squared plus z squared is equal to cl. x2 equal to cy divided by the square root of x squared plus y squared plus z squared is equal to cm. x3 is equal to cz divided by the square root of x squared plus y squared plus z squared equal to cn. X sub 4 equal to c divided by the square root of x squared plus y squared plus z squared is equal to c divided by d, where c is arbitrary for any c not equal to 0, and x sub 1, x sub 2, x sub 3, x sub 4 determines equation 1, x equal to x sub 1 divided by x sub 4, y equal to x sub 2 divided by x sub 4, z equal to x sub 3 divided by x sub 4, provided x sub 4 is not equal to 0. We have not assigned a meaning to x sub 1, x sub 2, x sub 3, x sub 4 when x sub 4 is equal to 0. But it is evident that if the point CL, CM, CN, C divided by D moves away from the origin an unlimited distance on the line whose direction cosines are L, M, and N, its coordinates approach CL, CM, CN, and 0. A little consideration will show that as a point moves on any other line with direction cosines L, M, N, so that its distance from the origin increases indefinitely, its coordinates also approach the point CL, CM, CN, 0. Furthermore, these values are approached no matter in which of the 2 opposite directions the point moves away from the origin. We now define x sub 1, x sub 2, x sub 3, 0 as a point at infinity, or an ideal point. We have thus associated with every set of four numbers, x sub 1, x sub 2, x sub 3, x sub 4, a point, ordinary or ideal, with the exception of the set 0, 0, 0, 0, which we exclude entirely from the discussion. The ordinary points are those for which x sub 4 is not 0. Their ordinary Cartesian coordinates are given by equations 1. The ideal points are those for which x sub 4 is equal to 0. The numbers x sub 1, x sub 2, x sub 3, x sub 4 we will call the homogeneous coordinates of the point. We now define a plane to be the set of all points x sub 1, x sub 2, x sub 3, x sub 4 which satisfy a linear homogeneous equation ax sub 1 plus bx sub 2 plus cx sub 3 plus dx sub 4 is equal to 0. It is at once clear from the preceding discussion that as far as all ordinary points are concerned, this definition is equivalent to the one given at the beginning of this section. However, according to this definition, all the ideal points constitute a plane x sub 4 equal to 0. This plane we call the plane at infinity. In like manner, we define a line to consist of all points x sub 1, x sub 2, x sub 3, x sub 4, which satisfy two distinct linear homogeneous equations, a1x1 plus b1x2 plus c1x3 plus d1x4 equal to 0, and a2x1 plus b2x2 plus c2x3 plus d2x4 equal to 0. Since these expressions are to be distinct, the corresponding coefficients throughout must not be proportional. According to this definition, the points common to any plane, not the plane at infinity, and the plane x sub 4 equal to 0 constitute a line. Such a line we call a line at infinity, and there is one such in every ordinary plane. Finally, the line defined above by two equations contains one and only one point with coordinates x sub 1, x sub 2, x sub 3, 0. That is, an ordinary line contains one and only one point at infinity. It is readily seen, moreover, that with the above definitions, two parallel lines have their points at infinity in common. Our discussion has now led us to an analytic definition of what may be called, for the present, an analytic projective space of three dimensions. It may be defined in a way which allows it to be either real or complex as consisting of points, all sets of four numbers, x1, x2, x3, x4, except the set 0, 0, 0, 0, where cx1, cx2, cx3, cx4 is regarded as identical with x1, x2, x3, x4, provided c is not 0. Planes, all sets of points satisfying one linear homogeneous equation. Lines, all sets of points satisfying two distinct linear homogeneous equations. Such a projective space cannot involve contradictions unless our ordinary system of real or complex algebra is inconsistent. The definitions here, made of points, lines, and the plane at infinity, are, however, precisely equivalent to the corresponding notions of the preceding section. We may therefore use the notions precisely in the same way that we consider ordinary points, lines, and planes. Indeed, the fact that no exceptional properties attach to our ideal elements follows at once from the symmetry of the analytic formulation. The coordinate x sub 4, whose vanishing gives rise to the ideal points, occupies no exceptional position in the algebra of the homogeneous equations. The ideal points, then, are not to be regarded as different from the ordinary points. All the assumptions we shall make in our treatment of projective geometry will be found to satisfy by the above analytic creation, which therefore constitutes a proof of the consistency of the assumptions in question. This the reader will verify later. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.